Hello again. We're back for part 3 in chapter 2 of the book, Describing Patterns in Data. This time we're going to be looking at one factor and one numerical variable, the relationship between two variables of those sorts. We'll also look at conditions under which it might be better to use the median and the interquartile range as measure of center and spread, respectively, rather than the usually more popular mean and standard deviation. We'll also look, for those occasions when mean and standard deviation are good to use, we'll look at the 68-95 rule, which is a great rough summary of what's going on in a distribution that's roughly bell-shaped. And in connection with that, we'll also discuss the topic of Z-scores. Before you begin your work, always check to make sure that Mosaic and TigerStats, your two major packages, are loaded. Okay, so how would we explore a research question where there are two variables of interest, a factor variable and a numerical variable, and the research question is about the relationship between them? Our example research question to begin with will be, who tends to drive faster, Georgetown College guys or Georgetown College gals? This is a question suggested by the data in the Math 111 survey data frame. It's certainly a question about the relationship between two variables. One of the variables, sex, is a factor. The other variable, fastest, is numerical. And we have this impression in our minds that once people know your sex, they culturally condition you to behave in certain ways, and this might include the ways that you drive. So we tend to think of sex as possibly causing, in part, how fast you drive. So we think of it as the explanatory variable in this case. Now, the idea for investigating the relationship between two variables really is the same all the time. You really want to find conditional distributions of one of the variables in terms of the other. So in a previous part, we looked at the relationship between two factor variables, and we found conditional distributions of one of them given various possible values of the other. That's what we're going to do in this situation as well. We're going to look at the conditional distributions of the numerical variable given each of the possible values of the factor variable. This means that we're going to be looking at the fastest speeds broken down into two groups. One for the value of sex equal to female, and the other for the value of sex equal to male. We'll get these two conditional distributions from our data, and we'll compare them. Maybe we'll compare their centers or their spreads or their shapes. And if the two conditional distributions differ in center, spread, or shape in some significant way, then the two variables are considered to be related. So let's take a numerical approach first. We have our familiar function favstats, but a little bit different approach to the formula part of the formula data input. Now the formula looks like the numerical variable, then your twiddles, then a factor variable. So the output of favstats looks somewhat like this, and we can begin to compare these true summaries of the conditional distributions of fastest. Here we have a summary of the conditional distribution of fastest given that sex is female, and here we have a quick summary of the conditional distribution of fastest given that sex is male. Let's focus in on measures of center. That's a pretty good idea. We certainly don't want to focus in on something like minimum. So certainly the minima do differ quite a bit, by 25 miles per hour actually, but remember that those numbers are probably based on only one individual from each group, one female going 60 miles an hour and one male going 85 miles an hour. We want to know what's up typically, so we tend to want to focus on something like means or medians. Let's try the means. So on average, the females were going 100 miles per hour. On average, the guys were going 113.5 miles per hour. So it looks like guys drive faster on average. When you make a conclusion like that, it's always a good idea to back up your conclusion with a couple of specific numbers from your output or your analysis. And so you would add a little phrase that compares the two means for the two groups right here. You can also look at the same thing graphically. One way to look at it is through what we call parallel box plots. So we call up our box and whisker plot function, but if we put in the formula fastest twiddle sex, then we'll get two parallel box plots. Fastest is along the y-axis. I'm afraid the label fastest is a little small here, but here you see 100 miles per hour, and here you see 150 miles per hour. And then along the x-axis, you'll get the values for sex, female and male. This may help you remember how to deal with this type of formula. When you read from left to right, you see fastest first and you see sex second. And when you look at the box plot, you see the label for fastest first, and then you see the labels for sex second. Sorry about that. We also want to give good names for the variable along the x-axis. We'd like to give a title, and I personally think that someone should have played with the y label and maybe given some units for the fastest variable. But again, we see the basic idea that the box for the guys, which represents the middle 50% of the guys, is higher than the box for the gals. So the guys are driving faster on average. The median for the guys, the dot here, is higher than the median for the gals. Again, that indicates that on average, guys are driving faster. There's a couple of outliers, but we don't pay much attention to them when we're trying to describe what's going on typically. You can also use histograms to describe the relationship between these two variables. The formula input's a little bit different. You still have your twiddles, and you still have your two variables fastest and sex, but the operator that separates them is a vertical line, which stands for what we call conditioning. Again, you have your data input as well, and you have something to talk about what's going to be on the x-axis. Again, it's a good idea to give units for the fastest speed. You have a title that's fixed by the argument main, and we would like some density histograms, so we specify that with the argument type. Let's see what comes out. The conditioning formula, that vertical line, produces two histograms that are side by side in separate panels. But these two panels both have the same scale along their horizontal axis. So we have this 50 to 200 mile per hour scale here for the females, and we have the same 50 to 200 mile per hour scale here for the males. It's just written up on the top, so it doesn't get in the way of the scale for the females. When we look at these two histograms, we can see that the females are mostly crowded around, maybe around 100 miles per hour, but the guys seem to be shifted a bit to the right from that. They're crowded around more like 105 or 110 miles per hour. We also see that their speeds are perhaps a bit more spread out. The rectangles are lower and more spread out, whereas the female rectangles are mostly higher here in the middle. So the guys are driving faster on average, but there also seems to be some more spread in their speeds. Now the graph looks pretty, but the fact is, with side-by-side histograms, it can be very difficult to compare the centers, because you have to look vertically, find a center for one group, and then go over and find another center, and then decide which is bigger. And this involves a lot of moving around for the human eye. So we tend to avoid this type of conditional plotting for histograms. And instead, if we would like to look at something like a histogram, you might want to consider density plots, but grouped. Now to get grouped density plots, you call up your familiar density plot histogram for the variable fastest. Again, in formula data input, you need to specify the data frame that fastest comes from. But you add in an argument Groups equals sex. Groups equals the variable sex that comes from the Math 111 survey data frame. And again, a title, something for the x-axis with units for the fastest speed. And if you add in auto.key is true, you'll get a nice legend that helps to explain what's going on. Let's take a look at the output of this. So by setting groups equal to sex, you get two different density plots all overlaid on each other in the same panel. And the auto.key equals true produces the legend that you see at the top that tries to tell you which density plot goes with which group. The darker color goes with the males, and the lighter color goes with the females. The two colors are also present down in the rugs here, but it can often be hard to tell much from what's going on with the rug. But from the density plots, you can see a lot at once. It seems that the women are again crowded around 100 miles per hour or even less, and the guys are crowded at something a good bit more than 100 miles per hour. So the guys are driving faster on average. Maybe you can also see a little bit more right skewness to the males' distribution as compared to the females. But again, that may be due just to one or two values. Notice that the 190 apparently went along with a male speed, and that's producing the bump that we see here, and that's a good bit of the tail. So I'm not so much sure that there's a great deal of difference in the skewness, but I definitely see the difference in the centers graphically through these grouped density plots. That's a nice tool to use. Now let's get on to that topic of deciding what are the best measures in different situations for center and spread. We've introduced two pairs of measures for center and spread. So there are two measures of center. There's the mean and the median, and there's two measures of spread, the standard deviation and the interquartile range. And they go in pairs. We tend to use the mean and the standard deviation together. We also tend to use the median and the interquartile range together. The question is, which pair is the better one to use? In order to answer this question, we need to think a little bit more about the properties of the mean and median in relationship to graphical representations of the distribution of a numerical variable. Here are some general facts. Half of the area of a density plot or histogram comes before the median. And secondly, a density plot or histogram will appear to balance over the mean. Let's see what we mean by this. Here's a more or less symmetric distribution, and vertical lines have been drawn at the mean and the median for this data. Now, when the distribution is symmetric, the mean and the median are going to be about equal, and in fact you can scarcely tell these two vertical lines apart. The median one is solid and the mean one is dotted. The mean is a tiny bit less than the median here, but you may not be able to see that depending on how you're viewing this in your browser. But it certainly is the case that about half of the area comes before the median, and it's also the case that if you thought of this density curve as maybe made out of cardboard and had been cut out of the picture here, and you wanted to hold your finger underneath it somewhere so that the curve would balance over your finger, you would want to put your finger just about here. And in fact, you would put it exactly at the mean. Now, suppose that the distribution is somewhat skewed. How do the mean and the median relate? Well, here's the median, and half of the area comes before it. But if you want this density curve to balance, you're going to have to hold your finger a little bit further out away from the median and towards this tail in order to create the balance. It's kind of like on a seesaw. If a kid sits way far off to the end of the seesaw, then they'll drag the seesaw down unless you move the central axis of the seesaw a little bit towards that kid that's way off. The mean is dragged toward the tail in a skewed distribution. So the mean and the median won't be the same when a distribution is skewed. Let's also think about what happens without and with outliers in a distribution. Recall that outliers are values that are a good bit bigger or a good bit less than most of the other values in the data set. Let's first make a small data set just consisting of these numbers here. And if we apply favestats to it, then we get this numerical summary. Now the median's 49, and the mean is about the same, 49.4. So both of them are about here, and they both seem to be about in the middle of the data. And if I were forced to give one number that described the typical data value for this set of numbers, I might say something around 49. So one is indifferent to the choice between median and mean when there's no outliers like this. But now, let's add on to this data set an extreme outlier. So what we've done here is we've created an object called new data. That's just the name I chose for it. What did I do? I put together a small data set with a new number, 200, using the C function. So new data has all of the original data set together with the new number 200. Now when we try favestats on new data, the numerical summary comes out like this. Notice that the median is about the same as it was before. Before the addition of the 200, it was 49. Now it turns out to be the average of 49 and 56, and that's 52.5. So it didn't change too much. But look at the mean. It's 64.5. The mean is now larger than all but the outlier itself. It no longer represents a typical value in the data set. So if I had to choose a measure of center for this data set, and I had to choose between the median and the mean, I think I would choose the median because it's more like a lot of the other numbers in the data set than the mean is. I would note also that when there's outliers or extreme skewness, the standard deviation can also be quite inflated. So the basic criterion comes down to this. If the data show really strong skewness, or if they have extreme outliers in one direction but not the other, then you should probably use the median in the interquartile range as measures of center and spread, rather than using the mean and the standard deviation. But if the data aren't strongly skewed and don't have big outliers, then you could really use either one. But a lot of people by default tend to prefer the mean and the standard deviation when it is acceptable to use it. One reason why people are so in love with the mean and the standard deviation has to do with our next topic, the 68-95 rule. Here's the idea. If the distribution of a numerical variable is roughly bell-shaped, so if it looks symmetric and unimodal, then you will find that about 68% of the data values are within one standard deviation of the mean, and about 95% are within two standard deviations of the mean. Almost all of them, about 99.7%, are within three standard deviations of the mean. Now, this rule is sometimes called the empirical rule, but I think we'll call it the 68-95 rule because that's an easier way to at least remember two of the parts. This rule works amazingly well, even if the data are somewhat skewed, although you've got to be careful. If the data are really, really skewed, then you'll find that the rule can look quite foolish. One way to see how well the rule works is to try it out using a Manipulate app that we've written into the TigerStats package. So for that, why don't we pull back to the RStudio server and give it a try. So first of all, we want to make sure that the package Manipulate is required. Let me look in packages and see what's up. So scrolling down, looking for Manipulate. It's not required yet, so I'll click it. And now it's loaded into the library and ready to use. The code require Manipulate would do the same thing. Next, we need to bring up the app imp rule. So I'll go ahead and type that into the console down here, imp rule. And it comes to us as a function that requires no input, so it just has these empty parentheses. Press the enter. And it looks like we're getting some graphical output here, so why don't we enlarge it somewhat. A little delicate operation. There we go. And there's a little wheel up here that says show the manipulator for this plot. So we'll click it and see what we get. And we get some options. Apparently we can vary the sample size that we're going to be taking from a certain population. Anything from a sample size of 5 to a sample size of 1,000. And right now it's set at 50. Also, the population that we're going to draw from could either be symmetric or skewed or really, really skewed. Let's start with symmetric. And why don't we show the density curve for the population that we're going to be picking this data from. Okay. Let's look over here in the plot. This histogram represents the sample of size 50 that we have picked from this population. This dot is the mean of that sample, so it's something less than 20. Here's the population itself. It's perfectly bell-shaped. These red lines represent one standard deviation less than the mean of the sample and one standard deviation more than the mean of the sample. It looks like they contain about 2/3 of this bluish area of the histogram in between them. So that's the 68 part of the 68-95 rule. And in fact, if we go over to the console, we see that the proportion that's within one standard deviation of the mean is 74%. So not too far off of the 68% predicted. Now the blue lines, they're 2 standard deviations below and 2 standard deviations above the mean. The 68-95 rule says that about 95% of the data should be within 2 standard deviations of the mean. What percentage was? Oh, about 90%. So not too far off. Now, the yellow lines are 3 standard deviations below and above the mean, respectively. They're supposed to contain within them almost all of the data. 99.7% or so. And in fact, 100% of the data was within 3 standard deviations of the mean this time. Why don't we try this again with a sample size of 1,000? So with a larger sample size, you might expect that the histogram for the sample more closely resembles the population, and it does. And look at this. Over in the console, the predictions that the 68-95 rule makes are almost perfectly borne out. 68% were within 1 standard deviation of the mean, about 95% within 2 standard deviations, and 99.6% were within 3 standard deviations of the mean. Now, of course, if you play along with this app, you're getting random data each time, so you're not going to get exactly the same sample or exactly the same numbers as I'm getting here. Let's try this with a skewed distribution, say sticking with sample size 1,000. So we can see the right skewness here. Here's the sample mean. And let's look over and see what's happened. Well, in the console, we see that the 68-95 rule did a surprisingly good job. 69% were within 1 standard deviation, as compared to a predicted 68%. 95% were within 2 standard deviations, and just about everything was within 3 standard deviations. Pretty good job. Maybe that was a fluke. Let's try it again. Well, looking down in the console, nope, no fluke. The 68-95 rule is doing a pretty good job. But let's try something super skewy. again, here's the mean, and 1 standard deviation, 2 standard deviations, and 3 standard deviations away from the mean. Let's check on the console, and oh my goodness, almost 90% of the data is within one standard deviation of the mean. So that's a big departure from the 68% that the rule predicts. The other two predictions aren't so far off, but as far as what's within one standard deviation of the mean, well, the empirical rule, the 68-95 rule, has been made to look pretty foolish. So you've got to watch out. You really have to have only limited skewness if you want to use this rule and have it be more or less accurate. Let's go back to the major PowerPoint. So how might you apply this rule? Say you have a population of people and their heights have some bell-shaped distribution with a mean of 70 inches and a standard deviation of 3 inches. You might ask, about what percentage of the people are taller than 73 inches? About what percentage are shorter than 64 inches? And here's a third question. The percentage that are taller than 74 inches is less than 1% and bigger than another percent. Less than U percent and bigger than L percent. Find U and L. I think what I'll do here is try out a little Manipulate app to answer the first two questions. And then I'm going to leave you to think about how you might use those ideas to answer the third one. So let's head back to our studio and look again. Imp Rule GC is the name of the app, so I'll type that in. Imp Rule GC. And you have to give it some initial information. You have to say the mean of the data, so that was said to be 70 inches. And you have to give the standard deviation of the data, and that was said to be 3 inches. And now we can try running it. And over in the plots appears a bell-shaped curve. And it starts off by talking about what's within 1 standard deviation of this mean of 70. Now, if you go 1 standard deviation back from 70, you've gone 3 units back to the 67. If you go 1 standard deviation above the mean of 70, you're going up to a 73. So the shaded area is telling you that about 68% of the heights are between 67 and 73 inches. Now, what percentage of people are taller than 73 inches? For that, you might want to look at what's outside. If 68% are between, then that leaves 32% to be outside, because 100% minus 68% is 32%. Because of the symmetry of a bell-shaped curve, half of that 32% should lie below the 67, and half should lie above. So you'll find that about 16% of this population is below 67 in height, and about 16% is above 73 in height. If you wanted to see what happens with 2 standard deviations, then since 95% are within 2 standard deviations of the mean, about 2.5% would lie below that, and 2.5% would lie above it, because 5% is left over after you take 95% out. So about 2.5% would be 2 standard deviations above the mean, and 2 standard deviations is 6, so 2.5% of the population would be 76 inches tall or more, and 2.5% of the population would be 64 inches tall or less. So you can answer lots of questions about what sorts of heights are likely or unlikely to be seen in a population if you know that it's bell-shaped and you know how to work with this empirical rule. In connection with the empirical rule, or the 68-95 rule, we have the notion of z-scores. Suppose that you want to compare an individual to a group. The z-score is a way of doing that. Now, the z-score for an individual data value, x, is simply the individual data value minus the mean for the group, that's what's in the numerator here, divided by the standard deviation for the group. It's called z, just a lowercase z. Now what it does is it compares how different x is from the mean of the group with s, the standard deviation, the typical amount by which a data value might differ from the mean. So it's telling you how many standard deviations x is above or below the mean for the group. Therefore, it's a measure of how unusual the value x is. If z is really big or a really small negative number, then that means that x is a lot of standard deviations above the average or a lot of standard deviations below the average, and that makes it unusual. In fact, let's just adopt a conventional rule for when to consider a value to be unusual or surprising. Let's just agree to say that a value x is surprisingly high if its z-score is bigger than 2, and surprisingly low if its z-score is -2. So here's an application of z-scores. Suppose that Linda is 72 inches tall. How does she compare with the other Georgetown College students in the Math 111 survey data? The way you would solve this question is to get her z-score. Now for the z-score, you're going to need Linda's height, 72 inches, which you have, but you're also going to need the mean and the standard deviation for the heights of the people in Math 111 survey. So you'll want to run favstats and look at the mean and standard deviation that come out. Here they are, about 68 inches for the mean and about 5.2 inches for the standard deviation. So to get Linda's z-score, you can just use R like a calculator. Here's the x of 72. Here's the x bar that was provided by favstats. And here's the standard deviation provided by favstats. Divide that standard deviation into the difference, and you've got about 0.75. So the z-score is about 0.75, or really 0.76 if you round it off well. So this means that Linda is only about 3/4 of a standard deviation above the mean height for Georgetown College students. She has a positive z-score, so she's taller than average, but she's not really unusually tall. Here's another question. Is Linda unusually tall for a female? To answer this question, we're going to need to get the mean and the standard deviation of the heights of the females in Math 111 survey. So one way to find that is to use favstats, but break height down into the groups depending on sex. So favstats height twiddle sex. And then we can read off the mean and standard deviation for the heights of the females in that group. Then we can plug into the formula for z-score. So here's Linda's actual height of 72 inches. Here's the mean for the females. And here is the standard deviation for the females. Do the division. And Linda turns out to be 1.55 standard deviations above the mean for a female. So that's more impressive. It makes sense. Females are shorter, so she would be more impressive when compared to females rather than to everyone. But still, she's not terribly unusually tall. One caution, though, is that when you compute z-scores and try to use them to describe how unusual a value is, that criterion for surprise really makes the most sense when the distribution is roughly bell-shaped. If the distribution is a little skewed, it's still okay to use z-scores to measure unusualness, but I would be careful. I wouldn't just use them on any distribution at all. I would look at a histogram or a density plot of the distribution and see how much skewness there is or how many outliers there might be. So that's the end of Chapter 2, and thank you for listening.